Hi. Might as well do one more gas law, right? We will talk about as many relationships as we can. So again, we've got our video here. It's called Avogadro's law. We'll get to that in a second if you remember the name Avogadro. This one, we looks like we have a scientist, and there's some information, so take notes.
Let's take a look at limiting reactants. Each of these flasks has 190 milliliters of 1 molar acetic acid. How many moles of acetic acid is that?
Let's not worry about that. We don't know what this is yet.
These balloons have differing amounts of sodium bicarbonate. 4 grams, 8 grams, 16 grams, and 32 grams. How many moles of sodium bicarbonate are in each of these balloons?
I'm not doing that calculation right now.
Can you determine the limiting reactant for each flask?
If you want, you can.
Acetic acid and sodium bicarbonate react in a 1-to-1 ratio to produce carbon dioxide. Let's do each of these reactions and compare the sizes of the balloons. First, 4 grams. Next, 8 grams. Grams.
Looks like the liquid's getting up into the balloon a little bit. It's also,
32 grams.
this reminds me of the Boyle's Law example we just did. Interesting. It kind of look. I'm not sure if the 16 gram and the 32 gram are the same size or not.
The sodium bicarbonate was the limiting reactant, so it could only produce as much CO2 as it had sodium bicarbonate. This flask, the 16-gram flask, is the stoichiometric ratio, so this is a perfect 1-to-1 ratio. In this flask, the acetic acid was the limiting reactant. These should be pretty much the same because they had the same amount of acetic acid, so that's all that could react.
I mean, it was off camera, so that's not super helpful. You know what? Let's not worry about the fourth one. Let's just think about the first three. So what we have another scenario here where we can now talk about this. If you missed the equation that I wrote, it's right there. And I think this is the most operative part here, right? We're creating a gas chemically. So that means that pre-reaction, I don't know how easily I can draw a deflated balloon, and post-reaction, there are different amounts of gas. Now amount is finally a variable. Given that this all occurred in the same lab, as far as I can tell in the video, I think the temperature and the pressure are constant because the pressure is like the external pressure in the room. So I don't think the weather on one side of the room varied that dramatically from the other. And then the variable here would definitely be volume. So amount and volume. We need to talk a bit about amount. I can't remember where is a good time to do this, but I might as well here. Amount, we are going to talk about amount the same way we've talked about amount, in previous units. Amount of gas, amount of particles is measured in moles. The variable is N, and the units, of course, are mole. The variable is V, and the units are liters or milliliters if you want, or even cubic centimeters if you want, because 1 cubic centimeter is 1 milliliter. So as long as the pressure outside and the temperature stays constant, the size of your balloon really depends on the internal pressure. And the internal pressure, don't forget, pressure is force over area. And force comes from number of particles and number of collisions. But if the pressure outside stays the same, that means that the balloon, if the pressure inside goes up, the balloon will expand. the area will increase at the surface until the pressure outside and the pressure inside are equal. In other words, the more particles you have in your balloon, the bigger it is, provided the temperature and the pressure don't change. And that's that. Hopefully you can see that here, where we got a certain number of particles, and if we have twice as many particles and 3 times as many particles, that the volume just goes up because as long as the temperature and the pressure are constant, the spacing, the average spacing of the particles seems to be the same. And so if you've got more particles, you need more space. So hopefully it's clear enough to say that this is a direct relationship. The more particles, the more space. Can either variable equal 0? Well, yeah. I think you could have something where n equals 0. But if we were to draw that n equals 0 container, I think the top would just be on the bottom here. It would be 0 volume. So that's fine. I mean, you can have 0 volume of a gas if there's no gas present. Right? That should make sense. That means if we have this direct relationship, yes, you'd have a graph that shows linearity, and based on what we've seen in our previous videos, that would be something like V equals N times K, or V over N equals K, or V1 over N1 equals V2 over N2. Hopefully we're starting to see some patterns emerge where the direct relationships go straight to this divided equation, and we start getting used to that showing up over and over again. There is a very interesting ramification of this, though. If our relationship is V over N equals K, there's 2 things that we can do. It says at constant temperature and pressure. Well, if we set the temperature and pressure to a certain amount, and we set the moles of the gas to a certain amount, the volume is just a function of that. You can see the number of particles dictates the volume. And so we get a very important number out of this. 1 mole of a gas at STP, shown below, occupies 22.4 liters of space. If you want to know how big 22.4 liters is, you can kind of imagine a cube about this big. I don't know if my hands are still in the camera, but it's about a cube about this big. I'm trying to think of how big that would be. I don't have anything in this room that's that size. I have this. This is a pepper plant I was growing over the last season. Looks like it's still alive for the most part. This bucket is about 22.4 liters. It might be not exactly, but it's close enough to give you a picture. If this was filled with just gas and not plant and dirt, this would be about a mole of gas at 0 degrees Celsius and 1 atmosphere. 2 things come out of that. Of course, I'm not at 0 Celsius right now, but that means you can figure out what the volume would be at this temperature, right? That's a combined gas law or a Charles law type problem. But more importantly, I said a gas. And the important part of Avogadro's hypothesis, Avogadro's law, is that it doesn't matter which gas it is. Any gas. Because the real thing is that the volume the gas occupies depends less on what the particles are and more on how many there are. Like I said, we're approximating air to be these monatomic particles. But you can see that most of the gas here is the space between the particles and not the particles themselves. So if you had a mole of helium or a mole of nitrogen or a mole of methane or a mole of oxygen or a mole of carbon dioxide, at STP, they all occupy the same amount of space. Of course, those gas samples would have different masses because the particles have different mass, but the number of particles in the container is the same each time. So in terms of how this looks when you see problems, it's less about calculation and a little bit more about recognizing that truth, where as long as you know the volume and the temperature and the pressure, you know the number of particles. As long as you fixed the temperature and pressure, you can convert it back down to STP, you know how much matter is in that sample of gas. Like, I can take a breath and calculate how much matter is in my lungs. I'm going to write that down. You can figure out the amount of air, the amount of oxygen and nitrogen in a breath based on this hypothesis, which is super powerful because now chemistry, like chemical reactions, can be folded into how gases behave. You can collect gas and calculate how much matter is in it, and so those problems where it looked like maybe conservation of matter fell apart, now it doesn't. So which two samples contain the same number of molecules? Well, same number of molecules would be the same temperature and pressure. So it's either, right, these two temperatures are the same, these two pressures are different. So we've got 100, 100, 2, 100, and then the same volume, right? So if you're at the same temperature and pressure, if the volumes are different, then obviously the amount of gas is different. But if all three of these are the same, then they're the same. So the answer here is A and C. And then at STP, which sample has the same number of molecules as 2 liters of methane at STP? Well, it's just the volume we're looking for. So if we're at the same STP, same volume, same number of particles. It's got, like I said, this is a jumping off point to a lot of stoichiometry if you wanted to, but I'm not doing that today. Thanks for watching.